Today we are going to do section 6.6 on page 753, parametric surfaces. Now the parametric surface is represented something like this. In our case, we will use the letter R. Whereas RUV, you notice that R is has three components, so it's a function in space like a field. But it's dependent on two variables. That's because R is not really a field. It's more like a surface, okay? Like normally when we parameterize with just one variable, that gives us a line in space. But because it ends up with three positions. And now we're going to do the same thing, except we have two variables, UV, which gives us a surface in space. All right, so that is our surface, which says that we have x, u, v, so x component, x, y, and z are all represented in terms of u and v, where u and v changes in some kind of a thing, some kind of plane, okay? You have rules on u and v, and with that, you end up being able to describe a surface. So please do example 6.58 for part of your homework. Where you are parameterizing a cylinder is something that we have done before, okay? But maybe not exactly in this exact description, but we have done something like this. So you can see what the book said. The book is still coming from the direction of back in the day when we don't have something called Desmos 3D, so we have to do this by hand, right? So you know certain things about it, but nowadays we'll just plug it into the 3D Desmos grapher, and then everything will come out very nicely. I want to show you some example of things that I graphed, and here's an example, and I would like you to graph this thing as well, okay? Here's the equation. Let's see. Okay, let me line this up so you can see it. Okay, this one is not checked, but that's the equation of the top surface. That is the blue thing up there. All right, and the equation is written like this. This is just the equation. This isn't the graph, and because it says SUV. The purpose of that is so that I can plot points on it. See, these are the points on the graph, but the equation, the graph is actually right here, which is the same thing without the SUV equals bit. Now, the graph is right here. This is just something I made up. As you can see, as U varies from 1 to 2, and same as V, then you get a section of that thing on top, and that is a parametric graph of this thing. So please do what I show you. I will talk about this a little bit later too. But anyway, so that is how we do a parametric equation. The details of how to parameterize is Desmos does have an excellent page to describe how to do it, and I have put the link at the bottom of this video. Okay, in the video description. So having said that, let's look at example 6.59 on the following page, where we you're looking at another surface. Again, this is a familiar surface that I think we've even done it before. There's something similar, but please do that one, or at least look at it as part of your homework. Next, we are going to, how do you find a parameterization? You just stare at it, and if it says x squared plus y squared, then you immediately remember x need to be our cosine theta and y need to be our sine theta, which in this case we'll call it x equal to u cosine v and y equal to u sine v. But everything else is similar. So please do example 6.60 as part of your homework. And then next, I'm now looking at page 758, which we have the sphere. Okay, that's the same principle. We have done the sphere several times. There's a specific parameterization to do the sphere. Something about cosine theta, sine phi, or something like that. Where to go? Doesn't matter. The point is that we have a way to do something like the sphere. Yeah, right there. Is in the figure itself, it says, remember the row cosine theta, sine phi, etc. That's how you do the sphere. So having said that, let's move on to page Oh, the next page, we have to look at some pitfalls. Okay, let's look at page 759, where we consider certain pitfalls. Now, a parameterization doesn't necessarily give you anything. Okay, your parameterization has to make sense. That is, for example, if you were to parameterize towards the bottom of the middle, whatever the page, where we consider this thing right here, okay? Your parameterization, our UV, has too many constants in there. So what happens is this thing doesn't go anywhere because you're not moving, okay? You only have V, and who knows what happens then. This is not really, this isn't a surface anyway. It's more like, I don't know, maybe a line, maybe who knows what it is. Okay, so to have a surface, you have to have enough requirements for your parameterization so that you even create a surface. So as a result, if the conditions, let's look at the next page, okay? For the parameterization, to make sense, the first definition is if you have a parameterization of something, it's regular if the RU cross RV is not 0 in the domain. So we are now on page 760. So the RU cross RV has to be not has to be not 0, because if it's 0, you're getting something odd. And then the next definition, the same thing. A surface parameterization is smooth if RU cross RV is not 0 for any choice. It's smooth, it's regular. I guess they said about the same thing. Well, the point is RU cross RV had better not be 0. All right, then your parameterization actually makes sense. Now, so with having said that, please do example 6.61 as part of your homework. But I want to point out one thing in the middle of the page where it says something interesting. It says, remember, right here where it says recall that the curve parameterization, our T, is smooth if our prime T is continuous and our prime T is not 0. Now, I don't recall any such thing, okay? It just doesn't, they never mentioned that, but this is something that you should sort of bear in mind. That is, our prime of T, specifically our prime T is not 0, then your curve is smooth, which means it doesn't have a weird corner on it. Let me show you an example that I drew. Now, for example, look at the purple line, okay, which is drawn right, parameterized by x, let's see, x squared, t squared, t4, t5. Now you notice that there's a corner there for various reasons, okay, and the derivative, our prime of t, does equal to end up being 0. However, you can have our prime of t equal to 0 and still works, like this the red line, okay, where our prime of I have a bunch of t's there, see, and where our prime of t does equal to 0, but it's still smooth. And you can plot these two lines in there to check out how things work. We are not really doing lines right now. We're doing surfaces, but it's good to revisit some of these things, especially and play around on the Desmos 3D, because we can, right? And so that's that. So example 6.61, you look at it and see if this thing has a corner or not, and so on. So please do that as part of your homework. And next, we are going to do the surface. Now, let's look at page 762, where we're considering the surface. Now, the surface, as we mentioned earlier, is you take some area in the UV plane, right? And you transform it through an operation. I don't know why I used S instead of R. Your book used R, but I happen to use S here, so bear with me and pretend that S is R, okay? It makes no difference at all. So anyway, SUV is a transformation that goes from UV, right? Take a little surface from the UV plane, and then you spit it over here, and in space where you get some kind of a thing over there, as my example earlier showed you. see this thing that I wanted you to plot, right? Is what you're doing is you have you start out, here's the UV plane, okay, and then you go through that transformation defined down here. Oops. Okay, the transformation defined down here, and then that will give you that blue area once you get through it. So that this is the same story. So we are going to calculate what that new surface might be. Okay, we need to know how big it is and how we might be able to calculate it. And the way to calculate the new area, which is on this side, okay, is this. We're going to calculate the vector. That is, this is this side is the original rectangle, and it has U0, V0, and then this is a regular rectangle, so it goes up to U0, V1, and then the other side is U1, V0. Okay, so we have, this is actually a little rectangle here. So transformed over here is no longer a rectangle. However, we are going to calculate at least approximate what the area of this thing might be, especially if the delta U and delta V is small. So to do that, we are going to consider the vector, okay? The vector up there from the original point, U0, to the result of, we'll do this one first, okay? The U direction. So we're going from U0, V0, SU0, V0 to the result of U1, V0. So that we are just doing the partial derivative. So what is the partial derivative? We can calculate it to be, we'll call it TU. T stands for tangent, okay? The partial derivative, which will be tangent to that line, is going to be, you just take the partial of each item, okay, FU, GU, HU, and so on. But we're going to go back to the original definition of the tangent, the partial derivative. The original definition says you will subtract the new point, okay? You will do the subtraction, new point minus old point, and divide it by the distance, which is delta U in this point, in this part. And then you do so by doing the same thing to all three component functions. All right. Now, if you look at this thing, what is that as delta U go to 0? That's approximately the partial derivative, because we're only changing U, right? U goes from U1 to U0, and V is not changing. So that's the partial derivative definition of the partial derivative. Now, if that is the case, that means that we can multiply. See, we're doing dividing by the delta U right here. We can just keep this thing and then multiply delta U to the other side, which means delta U times the tangent. It happens to be the length of this vector, okay, that goes from the old point to the new point this direction, and that is the TU is as long as this. And similarly, TV is going that direction, is tangent in that direction, and is as long as that distance. So then the area here can be approximated by the cross product. Okay, you remember the cross product equals to the area of the parallelogram that the two vectors define. Okay, you have two cross products, so the areas, two vectors, the cross product, the magnitude of the cross product equals to the area. So, and therefore, we have this part. See, one vector is delta U TU, the other vector is delta V TV, and therefore the area of this thing is going to be TU cross TV, the magnitude, times delta U delta V. And with that, that is how we derive at calculating the area of your resulting parametric surface. And to be exact, let's look at definition on page 763, which is where we are right now, where the area is given by TU cross TV in magnitude, and then times dA. That is, see, as you can see here, TU just happens to be the length of TU happens to be the length of that little transformed rectangle, okay, the same as delta TV, and therefore the area is TU cross TV, and then dA, where over the domain, original domain D, okay, and that will give you the area of some surface. Now be very careful when you do this, however, and I want to make this very clear. That is, this is, okay, this is where's the domain? The domain is this rectangle, okay? Because normally when we consider a function of a surface, we think of the domain as that shadow on the bottom on the xy plane, right? But as you can see here, that shadow has nothing to do with the domain. We have gone past that. We're doing parametric equations, and that means the domain is in a different space, in a different universe, okay? It's not related to this space at all. So the domain is a perfect rectangle, whereas the range is that blue thing, and the range might have a shadow on the ground, but it's got nothing to do with it, okay? So our domain comes from here, and then our function lands here. And that's how all this stuff makes sense. Please try to graph what I did, okay? What I did here is that I tried to figure out, okay, that is the function, and I figured out the points on 1, 2, 1, 1, 2, 2, 1, 2, and 2, 1. See, this part is where I scroll down and it can't show, so I put it up here. Now, please plot these points. Look how smart Desmos is. It's able to plot you some points, okay? It's able to plot the surface and make it blue, and then also plot the bottom. This is the bottom surface. How do you plot the bottom surface? You just do the same equation, except that it's equal. The z component is 0. If you do that, it'll give you a little gray shadow right down there. And also plot the bottom points. Okay, here are the bottom points. The bottom points are the same as top points, except with the z component 0. See, then it all fell down to the ground, and then everything looks very nice. So please try to plot this thing. It's a lot of fun, and it helps you understand parametric equations better, and also how to enjoy the Desmos 3D calculator. So now that we know the formula for calculating the parametric surface of something, and then the formula being the integral tu cross tv, okay? Tu is the tangent, and it's just given by the function, the partial with respect to u, and the same as tv. And it should be called ru, but we call it it is ru, but we also call it tu to emphasize that it's the tangent. So the thing has two names. All right. So then, okay, so seeing that definition, please follow that formula and do example 6.62, and then, yeah, which calculating surface area is almost never easy, no matter how you do it. So it takes a while, but it's just algebra, okay? Put in your time and do the algebra, and don't mess up, and then you will get the right answer. Again, next 6.63, calculate more surface area. Please do that. And then next 6.64, yet more surface area. Please do that. And that is, and we have come to page 768, which states, now we're going to do the surface integral, okay? Which is more interesting than doing surface area, being that we've already done surface area many times, right? So but this is just one more way of how to calculate the surface area. So next, let's look at page 769, where we consider the scalar surface integral. The scalar surface integral is just like calculating the area, except that now, instead of just doing the area, we're going to stick a function in there and make you work harder. So please look at, here's 6.19, okay, the equation to calculate scalar surface integral. You stick a function in there and you integrate. So your integral is over the surface S, okay? And how do you do that? You plug into that formula next to it. That is, you calculate tu cross tv. Remember, tu is just the partial derivative of r with respect to u. And yeah, r is whatever it is, okay? And so is tv is the partial derivative, and they represent the tangent. That's why we call them t instead of r. And then you plug the function in there, and then you integrate that whole thing over the area d that your surface is referring to. So having said that, please do example 6.65 as part of your homework. It's just a matter of plugging in the formula, really. Now that you know what's to be done, yeah, your only job is just to do it. It's nothing that you haven't done before. By that, I mean you have you haven't done the cross product and then integrate before, of course, but other than that, but you've done the cross product and you know how to integrate, and you just, do that. So the work itself is nothing new. So that's example 6.65, 6.66, please do that, and 6.67, in which, as you can see, these things, it can get quite complicated. But, well, maybe, and maybe not quite complicated isn't the word. It's more like long, okay? Because you got to do the cross product, and you hope you don't mess up. And I messed up a lot. I'm always messing up the cross product, which means it took me like 3 or 5 times longer to do a problem than it should have. But anyway, please do that, okay? And try not to mess up like I did. Don't do as I do as I say. And then, but yeah, you keep getting 6.67. Next, what's that? Example 6.68, where you are calculating the mass because you're giving some density. Well, the density is just that random function that we're going to stick in there and make your integration harder. Well, it might not get harder, or it might, who knows? But please do that as part of your homework, as a character training. See, doing all this big pile of work is going to build your character like you wouldn't believe. Next, let's look at example, let's see, page 774, where we talk about the orientation of a surface. The orientation means that any surface, let's say here's your surface, okay? Imagine a normal vector that's sticking right out of it, like this. Here's my normal vector. The normal vector tells you which way the surface is facing. If it's facing up, or side or down or whatever. But the normal vector you could stick it either direction, like a surface has 2 sides. Which side is it going to be? And that's what the orientation is talking about. Basically, is where do we put the normal vector? And well, sometimes your normal vector might come out one way or another way. But anyway, so that's what it means. Now, in the meantime, let's look at the next page, 775 at the very bottom. So the normal vector is defined by the cross product. This is the unit normal vector. So it's the cross product divided by itself. Okay, well, when you have 2 tangent vectors and you will cross it, right, that will give you the normal vector of the surface, where the 2 tangent vectors well, in our case, we are taking TU and TV of our surface representation. But basically, for a surface, you take the 2 tangents, which are in the plane, and then you cross it, okay, by the right-hand rule. The normal is perpendicular to it, and that gives you the normal vector. And then when you divide it by its magnitude, that gives you the unit normal vector. And that's what that is. Surface has 2 directions, either up or down. So let's not make too big a deal out of it, right? And so please do example 6.69 as part of your homework. And then we'll go to the next thing, turn a couple of pages later, and we go to page, what is that? 778, where we are talking about the surface integral. Okay, the surface integral is something that we will call the FDS. Now, what does it do? What happens is that we call it the FDS. This is the first time you see it. Please look at this for a second, so that I want to explain something. Okay, here's the surface integral, which means you have some function, some vector field, and you're dotting ds. The s is boldface. In other words, s is like a vector. But what is the boldface s? It means on this side, right here. Okay, the d boldface s is the same as nds. That is, your surface has a direction related to it. So we write it this way as a shorthand. So ds boldface means that the normal vector times the regular ds. Now, sometimes your book is inconsistent in the usage of that. They might put a boldface on this side. That is, you have both n in boldface and the s in boldface. But what it means, but we stand by this equation, okay? That is, the d boldface s just means nds. is because the boldface means it has both the value and a direction to it. And where's the direction? Is the n, okay, the normal unit vector. Right. So the definition as given is that if f is a continuous vector field and domain contains the surface f s, which has the unit normal vector n, then the surface integral is defined like that. And so let's look at the next page. Well, it's defined like that, but what are we supposed to do with it? Okay, here's how we actually calculate it, which is on page 779. Now, please pay attention to this part because that's how you're going to be doing the homework. Because, you know, this is all very good, but what are we supposed to do with it, right? So here's what you're supposed to do with it. What you're going to do is notice that the f.nds is the n is defined as the cross product of the two tangents, tu and tv. And the t's, how are the t's defined? The t's are defined like by r, okay? R is related to your transformation, your surface, whereas r, that is partial derivative of ru, is equal to tu. They just call it t because it's a tangent, okay? It's actually ru, the partial r, partial u, and the same as tv. So anyway, so we have that dot product, which is the same as plugging this thing. The ds is the same as from the surface area. We know that ds is equal to tu cross dv magnitude dA. Okay, that's something we did just a few pages ago when we did the surface area, and where we proved that ds is equal to the cross product times dA. So then once you have that, then you can cancel out the magnitudes, and all you have left is this equation right here. How do you calculate the surface integral? By doing this, okay? You're going to take the dot product of the cross product and stuff, and then you integrate over some domain D, and that is the equation that you will be using. And this is equation 6.21 for the surface integral, okay? So anytime you see this equation, that's what you're going to be doing with it. So having said that, as you can imagine, that doesn't look like very easy, and it's not. But you can do it, okay? It's just the same thing that you've done before. You take the cross, you calculate the tu and tv, and then you have to take the cross product, and don't mess that up because I did many times. And then you do the dot product, and then you integrate, and then maybe some answer comes out that's actually right. Okay, so with that, please do example 6.70 as part of your homework. The same as the next one, 6.71. Do that. 6.72, yeah, the same thing. Now, for example 6.72 on page 781, we have the f. They give you f is some other thing. I don't know. K delta T, it has to do with heat flow. We don't care if it's heat flow, okay? Just plug it in and crank it out. We're not interested in what all this stuff means because we're only interested in the math, okay? And some other fields, such as physics, can make some meaning out of it if they want to. So that is, as you can see, the heat flow is no simple matter. Well, it goes on. It's just lengthy, okay? It's not particularly hard, I don't think. Well, actually, I think what's happening here is you have to worry about the heat flow on 3 surfaces or something. In other words, you're getting 3 problems for the price of 1. Isn't that great? So please do example 6.72 and give yourself 3 times the time, okay? So that you're not surprised that why am I stuck on the same problem 3 hours later? Because it takes time to get through this type of thing. So with that, we have come to the end of this section. For homework, please, which is on page 784, please do problems 275, 77, 83, 91. 91, the answer in the back is a little bit off, okay? I think you will be able to see it when you do it. And 293, 97, again, the answer in the back is a little bit off, I believe. And then 303, 313, 317, and 323. It took me a whole lot longer than it should to do the homework. Why? Because I'm always messing up the determinant or something. It was a mess. But I did get through it, so should you. So please go do your homework, and when you get back, I want to talk about some of them. Now that you're done with the homework, let's talk about it. First, problem 283. We have, let's see, some surface. Oh, we're integrating some function over the sphere. Okay, so what I did is I just copied from example 6.67. I wasn't going to do this. I mean, imagine how painful this would be. So I copied this down from example 6.67, and I'd probably be messed up if I had to do this. But anyway, it says that t phi cross t theta equal to whatever that is. And in fact, that's even not the shortest point. It's just equal to 4 sine theta. I mean, 4 sine phi. See, that's the real answer, because there's a situation where sine squared is here and cosine squared is here, so it becomes 1, and you take the square root. And being that phi is in the first is less than 90 degrees, okay, pi over 2. Therefore, you can just take the square root and don't have to worry about the absolute value, which you do have to think about. Okay, anytime you take the square root of something, check to make sure that everything is positive. Otherwise, you might run into problems. But anyway, so we don't have a problem here. So once we got this, we follow the formula, which is something about, where's the formula again? Well, it's somewhere. Okay, I think here it is. I wrote down the formula here on page 779, where you just plug everything into the function, take the dot product of the cross product of tu cross tv, which end up being this mess, right? And then I think I messed up somewhat. So at first I couldn't get the right answer, but eventually, or something, I don't know. But anyway, eventually I got the right answer, and that was right. And I don't even have to do a very tough integration either. See, just that thing, which is whatever it is, 1/4 or something. And then I got the right answer. And which, so after I plowed through all that, I'm very proud of myself. So next, let's look at problem 291. Where we have, some surface and some function, and we're supposed to integrate something over something. Now I follow the formula exactly like they say, and well, the answer in the back says 3 square root of 4, which is weird. Why would you say square root of 4 anyway, right? It's just 2. But anyway, so I found out it's slightly different from this. Anyway, so let's look at this thing. How do we do this? What we have is tu cross tv. And then, so I did the cross product, and I might have been slightly wrong, but it doesn't matter because I just have to know the magnitude, which I think saves me in some problems. So I didn't have as many mistakes because I just calculated the magnitude, which is okay. And then I plugged everything in here, okay, and everything was okay until I got to here. See, is supposed to be 6 minus up here, see, 6 minus 2u plus 3v. When I got down here, for some reason I wrote down 6 minus 2u plus 2v. So then everything got into a mess. I couldn't get the right answer, so I come back and notice, oh no, it's 3v. So when I put 3v in, then life got a lot easier. Suddenly it's only integrating over 6u. That's it. Look at that. How comfortable. So I did that, and I got the answer of 3 square root of 6, which makes sense because the answer claims 3 square root of 4, and they probably just mistaken and typed in 4 when they just mean 6. So that's the end of 291. Next, let's look at problem 297, where we have, I don't think it's a pretty standard. I don't know what we're doing here, but we'll just plug everything in. And so the surface is, I parameterized it as s, u, comma, v. I don't know why I use s. I think the book used r. I must have had my brain stuck on s stands for surface or something. Okay, just remember when I use s, I just mean r. There's no difference. And one's as good as another. But anyway, so then we calculate the tangents, which are the partial derivatives. We calculate the cross product, which in this case, part of it becomes 1, which is convenient. And then eventually we take the square root, and we can just calculate it equals to this because u is bigger than 0. Because in the parametric representation, you notice u is on this line, u is bigger than 1, okay, less than 4. So it's okay to just get rid of the square root sign and not worry about it. And then continuing, we plug it into the equation, right, with the proper limits, stuff going from wherever what is that? Whatever it is. Okay, v goes to, u goes from 1 to 4, right? Okay, so anyway, we plug that in, and then we come up with this two integrals, because we can separate them, because u and v are not stuck together. So we just break it into two integrals, and this integral happens to be pi. And that's just a side notice, because we did this in calculus 1, okay? We know that from 0 to 2 pi, if you're integrating the whole range, this value being that inside is 1, then it equals to 2 pi. So each one of them equal to pi, because cosine and sine are identical in terms of area when it goes from 0 to 2 pi. Anyway, that's just a sideline that doesn't really matter. Or you can just calculate this thing the normal way. Either way, this value equals to pi, and that thing equals to whatever that is. And then by the time I'm all done, I came up with this odd-looking answer that turns out to be correct. Yay! Oh, the reason I say that the answer in the back is slightly wrong is because the square root here, it went over the pi in the answer, but there's no way that's possible. I think that's just a slight typing mistake. Okay, the square root only goes over 2. It shouldn't go over pi, because pi is this integral. There's no reason to take a square root of it. So that's that. And then next, let's do problem 303, where we are doing the same or similar things. We're doing f dot nds, which is we'll just plug everything in and follow the rules. Okay, the rule says we got all the stuff. Okay. Oh, the first part is we need to consider parameterizing the triangle area that we want. The way we do it is check example 6.65, which is shows you how to parameterize something like this. Okay, a similar problem. Well, all you do is you let u go from 0 to 1, and you let v goes from 0 to 1 minus u, and that will get you that entire triangle. Okay, and so then we figure out what tu and tv is, and here's where I messed up. Here's a very simple cross product, right? You just have to, I mean, it's 1, 0, but for some reason I messed it up like 5 times. I could not, well, I should have written it out like this. Eventually I did and got the right answer. But until then, I was subtracting by minus 1, 0, and I was missing the column. It was a mess, okay? I do not like doing determinants. I'm always messed up. I should have written it out, but you know, it's just 1 and 0. Why should I work so hard? I mean, I can do it in my head, until I couldn't and screwed up. Ugh. But anyway, after 5 times to finally be able to get this cross product come out, then the answer actually turns out to be pretty simple. See, here's our integral, which is uv plus 1. You integrate on the triangle like that. And so I did it by hand and came up with the answer, which is correct. But I also did this on the Wolfram calculator, and integral calculator, which is very nice, and I want to show you because I've never done this before on this calculator. That is, you notice we're doing a double integral. See, to do the double integral, you have to pick the tab I show on that side up there, and then choose the double integral tab, and they even let you choose what variable you want. Isn't that nice? So I was able to type everything in exactly as is. See, dv, du, all those things, and so then that gave me the answer, just like the back of the book. So if you ever need to do a double, and they even have triple integrals, you can just do that. So that is that, and one more problem. And finally, let's do problem 317. I think is something, I don't know, same thing we've been doing. Okay, we have a surface S uv, which is parameterized that way. All right, and then with those limits, u goes from 1 to 3 because that's what they wanted. And then we take tu and tv and we do the cross product, and it end up being something negative. When you see negative, it could mean that it's pointing down, okay? And I think the book wants us to make it point up. How do we do that? We just flip all signs, okay? Just flip it around. So then what was negative is now positive. And then we do follow the formula and do the integration and come up with some answer that is positive. So that is the right answer. And with that, we have come to the end of this section.